Events, and then we'll take a break, so bear with me for a little bit longer. I know this stuff can be a little dry, and we're not seeing where this is coming into play, but I think I got a pretty good example at the end of the section or the next one, I forget. So let's talk about it. All right, I need to move this down still. Independent events. Let's talk about independent events. So things are independent if we have one of these conditions hold true. So basically what these conditions say, particularly the top two, is that given, right, so this is the probability of A given B, right, saying it's equal to the probability of A. So given that B occurred, it does not change the probability of A happening, is what that says. If B occurred already, we knew B occurred already, it had no effect on what the probability of A was. So that is independent. It is independent of A because it didn't change the probability. I'm having a problem remembering how I talked about this in an example before. The go-to method is cards, playing cards kind of thing. If I'm playing cards, so if I have an example of I have cards, I'm giving out cards. You pick a card and it's an ace. That's going to change the probability of getting another ace or another card in general because I pulled the card out and put it aside. So here we're having an idea of without replacement. I'm not replacing that card. But if I took that card, that ace that you put it back in the deck, and I try and pull again, I have the same probability of pulling that ace. It didn't change my probability of getting that outcome. This is the idea of independent. That's an independent event. Pulling an ace once, sticking it back in, and then trying to pull it again. I have the same probability whether I was given that first card was an ace or not. So independents are events, and this is how we tell. This is how we check if things are independent. We have a couple examples at the end of this section where we actually test for independence, that things are independent from each other. So I'm still trying to think of an example, and I can't come off the top of my head with a real world example besides mathematics and dealing with cards and dice and stuff. Rolling one fair dice, right, and then a second one. Doesn't matter, I got a 6 on the first one. The second one, I still got a 1 out of 6 shot to hit whatever I want. Okay. Right, those are independent events. One does not affect the outcome of the other. So, two events are independent. Writing in my binder over here. Forgot where I was supposed to write. Two events are independent. Maybe I should close this up and not have this on the same page because I'm going to do that over and over again. Two events A and B are independent if the knowledge that one occurred does not affect the chance the other one occurs. So chance is synonymous with probability, percentage, stuff like that. For examples, the outcomes of rolling 2 fair dice, just like we talked about, to show two events are independent. We only need to show one of these things to be true. Typically we show this one or this one, kind of thing. So that's what we'll do today, to show things are independent.
So you can do that with anything? Like you can use
Yes.
that with pretty much anything?
Yeah, we will see where we can use it. All right. So sampling with replacement. Or without replacement. So that was, again, the idea of pulling cards. So I can pull the cards, set them aside, pull another card. That's without replacement. I'm not replacing the cards with replacement. I would then take that card, give you that card, you look at it, and put it back in the deck. I replace that card. Same idea, but right with replacement is the idea of independent. We have independent events. If it's with replacement, but these are dependent typically when we're talking about without replacement. Right? Usually that makes things happen. Usually that makes things dependent on each other. So if I pull that ace and I leave it out, then pulling another ace or even another card, it changes the probability because I only have 51 cards at that point. But with cards, right, 51 cards is a small little change. So we thought, right, of a lot of our probabilities that we deal with in the real world, like pulling a Democrat out of all of Americans. So kind of thing, the probability of me randomly, right, kind of thing, I pull that person out, but then I think again about pulling another person. What's the chance that I get a second Democrat? That's without replacement. I'm not putting that person back in the pool, but I don't have to worry about that in that case because we're talking about such a large population that it really doesn't change the probability of me getting another Democrat or not. Right. Versus if I do it in this classroom, right? I pull somebody out, right? Here's a Democrat, right? That changed the probability. I pulled that person out because I really only have like 42 people in here or something like that. That changed my probability of getting another Democrat the second time I pulled it. So in small samples, right? Small populations, it can be effective on our probability. So what I'm talking about is essentially a large numbers law that comes into play with independence. We can consider two events that are typically dependent to be independent because we have such a large population and our sample's a lot smaller. Does that make sense? So, think about that Democrat. This is what we do a lot of times. A lot of our probabilities are actually dependent, though if it's a large enough population that we're pulling from, then it doesn't really matter. Okay. Nas.
So just really quick, a question about the independent. Does the fact that something's independent or a situation independent depend on like the population size never changing, like the deck of cards? So like if that population's like, or that sample size
Yes.
never changes, like a deck of cards is always gonna be this number?
52.
Does
Okay.
that make it like
It's
independent?
yeah, it's kind of, so if you're putting back in, then that's always 52. So if you're pulling out, right, and then put that card back in, it's always 52. I pull out an ace though, typically the way real cards work, right, you pull out that ace, you keep it, right, and then you don't have that ace anymore you
Right.
can pull from. So
Okay.
that changes the probability.
I see,
So that
okay.
is a dependent event.
Okay.
We should consider it as a dependent event of our probability, I think.
I guess I'm just trying to look for like little tricks or clues, like to make it
Yeah.
for sure.
Hopefully we'll have something here we can talk about. So, if it is not known whether A or B are dependent, independent, or dependent, assume they are dependent until you can show otherwise. So that's just a safe bet, right? We can assume something's dependent. We're just being safe and making it clear. So so here's an example. We have one fair, well shuffled deck of 52 cards. It consists of 4 suits. Did we do this last time? Did we do cards last time? Did we bring up the deck of cards?
Cards or dice or.
But I don't think this is the same thing, right?
No, it's just, I just want to make sure that we know what a deck of cards looks like, you know, so.
Yeah, you did show us.
Yeah, okay, I brought it up, okay, thanks. I just wanted to gist of what it looks like, because this isn't a big question. So there are 13 cards, each suit consisting of one, right? One is an ace, typically, and then you have 2s through 10, right? A jack, a king, a queen, right? And you have 3 suits, so hearts, clubs, diamonds, spades,
Yeah, you
stuff like
showed
that.
us it.
Okay.
There's a lot of people that's making sure we got it. So suppose we pick 3 cards with replacement, so we are replacing that card. The first card we pick out of the 52 cards is a queen of spades. You put this card back, reshuffle the cards from the deck, pick a second card. It is a 10 of clubs. So you put this card back, reshuffle the card, the third card you pick, this time we get the queen of spades again. So, right, so what it's saying is basically we're putting those cards back, we have a chance of getting those cards again. It did not change the probability or any outcome of getting those cards in any way, shape, or form. So you pick each card from the deck. So these are independent events. We're talking about independence.
Independent equals with replacement.
So this is just an exercise in trying to get you to see whether something
Yeah.
is independent or.
Yeah, it's not really an exercise, it's just talking.
Alright. Well, because here it says.
Kind of
you-
what I said.
It says you can try it, I'm like, okay, so are we doing?
So, I don't know.
I'm not like a big fan of I
No.
don't
Me neither.
do Vegas and all that too much, but I do
Yeah.
know when you go there and like when they're playing yeah, they use like 5 or 6 decks that
Yeah.
they put inside the
So how do we
little-
calculate that probability?
So-
Are they mixed up? I don't actually know if they mix up all 5 of those decks either, because that would be weird, because you could possibly get 2 ace of hearts and a blackjack scenario, right?
Cause it's more than
So
one
I
deck.
think
that
they
you use.
mix up the cards and then they stack each deck on top of each other, so you're not getting repeats. So maybe they have some kind of layer that says, okay, that's the end of this deck. I don't really know.
Okay.
So how
Yeah,
they
but
how they
I'm like, wow, they
differentiate
making
between
it-
one deck and the other.
Making it impossible.
Yeah.
Your probability to get 21. If they doing it that way, okay.
Well, it would be the same probability, I think, whether you have 5 decks or 1 deck.
It's still the same.
So, because, right, you have a portion of aces and 5 decks that you would essentially in 1 deck. Right, out of the total number of cards. Because you would have 4 in each deck.
That's if all the decks are not mixed together, or would that matter?
I don't think it really matters, actually. I think I said that wrong. Because if it's mixed together,
It's
yeah,
still-
you could get it, you know, the possibility of more aces in the top. So maybe. I'd have to think about it. Let me think about it. But
I just know they use more than one deck.
Right.
So I was wondering.
But we are aware that the house wins all the time, right? You know that, right? Just look at Vegas and those buildings in Vegas, right? These big, beautiful buildings they got, right? They make money. That's how they make money.
I just want to
Yeah.
clarify my understanding. So basically, if replacements, that means independent.
Yeah.
If not replacement.
If not replacement, without, yeah, dependent. So, so without replacement, if we don't put those cards back in and we keep them, then we're talking about dependent things. So, again, examples, right? I pulled 1 card out. We pulled the King of Hearts. We put this card aside and a second card from that deck. We have 51 cards remaining, and we get the 3 of diamonds. But it doesn't matter what we get. It's just that we keep losing cards, so the denominator is changing as we go. Right, my sample space is decreasing as I go because I keep pulling cards out. And that's the idea of counting cards, right? You're actually counting the ones that are missing, technically. All right, so where was I? I don't know why I'm going that far down. All right, so let's talk about the next example. So you have a fair, well-shuffled deck of. Oh wait, I was supposed to take a break, wasn't I?
Yeah, that could be nice.
Yeah, let's take a break. Why don't you read over this example, try and figure out this example while you're taking a break.
Like a break or like a break to read that thing?
Sure.
Um,
The